produced by heavy ions.
Thank you. Are you hearing me fine? Okay. Well, first, let me thank Sonia, Tobias, Nico, and Carlos for organizing this workshop. It's very nice, and also to having the school the week before, and also for supporting the student. This kind of event is very important for our community. Thank you for having this, and also thank you for this invitation. Well, when I got this invitation, I had a little bit hard time to think of something that would be interesting for this audience, and also learning that Lubian would talk just before me. So I would like to talk about hints on nucleon-nucleon correlations from the experimental point of view. So I will take for granted some of the things that Lubian has talked just right now, and just make some overview. My main point here is that I'm going to discuss some results on two-proton transfer and on silicon-28. And the main question, I think that the punchline here will be how from nuclear reactions we could or not, I think is still for me an open question, but how from nuclear reaction, from two-proton transfer reaction, can we get some insights for this pairing correlation between nuclei? So, well, I like to start my presentation with something to remind. And pairing is a very important feature of a nuclear medium for the mean field of nuclei. So even nuclei is 0 plus in the ground state. So this gives us the pairing between proton and the neutron is a very important thing. Well, just we could imagine ourselves as a penguins in Antarctica, and we couple together. So what happens if at some moment one person outside of this group of penguins push? Is the other penguin going along or not? So this is the main idea that I would like to discuss from the experimental point of view. Okay. So the summary I would like to say is, well, I'm going to explore this feature of nucleon-nucleon correlations using heavy ions, which from experimental point of view is not a very good choice at the first glance. Well, I would give you some pros and cons on that. Some previous work, just briefly, I'm going to mention this first work that we have measured with our colleagues in Italy on oxygen 18 and carbon 12. And from that initial work, from the cross-section, we started to grasp these information on these correlations for neutron-neutron correlations. And then I will dive in these results for silicon-28 and oxygen 16. So this is my main focus here will be on this data here, and how from the experimental point of view, I think, and just to be clear, I'm still open to critics, but I think we might get some information on these proton-proton correlations, right? So isospin symmetry, I would like to start with this. Nuclear structure model often assumes that these nucleon-nucleon interactions are nearly the same, nearly similar between proton-protons, neutron-neutrons, and proton-neutron pairs. Okay, so this means that well, I just going very quickly on this. This means that we might have this kind of feature here, and the interaction between this kind of situation here are nearly the same. So just to make clear, I'm not focusing on a very short range correlations in which we have this difference between proton and neutron. I'm not, and this is a very nice paper, almost 20 years ago. Right? So the thing is, I would like to address here is how these neutron-neutron, proton-proton, and proton-neutron correlations manifest in heavy ion transfer reaction. This is my main point. So I'm not, and I try to be very careful here. I'm not saying things related to the short range correlation. So a few words about transfer reactions here. Well, and also I'm experimentalist, and I would like to emphasize here that this is a research in which we must have not only theoretical, very strong theoretical on the reaction models, on the nuclear structure models, but also a very good quality on the experimental data. So, and from the experimental nuclear toolbox, we can measure elastic scattering, inelastic fusion, nuclear transfer. Lubin mentioned about fusion, nucleon transfer, breakup. So all of these reaction channels are inside this toolbox for the experimentalist. The idea here is some of these reaction channels give or put constraints on the input used for these reaction calculations. So for instance, when we look back on the elastic scattering, we may constrain the optical potential that is used to not only to calculate the elastic scattering, but also the inelastic and the transfer reaction. So the main idea here is trying to take a look and establish a common ground for this theoretical framework. Well, from the nuclear structure point of view, the nuclear wave function could be, we can slice this wave function as the single particle term, a collective term, a pair term. So when we are measuring one nucleon transfer, we are pinpointing this part of the wave function. When we are measuring the two nucleon transfer, we are selecting and bringing to the first place here this part of the wave function. So when we are measuring 2 alpha or 1 alpha transfer, we are selecting a part of the wave function that describes the nucleus. So I'm not saying here that because I'm measuring the 2 proton transfer, I'm saying that the nuclei is composed by something, a core plus 2 protons. Just saying that I'm measuring the 2 protons, so I'm looking at this part here of the wave function here. And the main ingredient on these kind of calculations are what is so-called the spectroscopic factors. Some of the theoreticians also use these ANC, asymptotic normalization coefficients. They are more or less the same, and I'm not going into details about that. Okay. So, and the basic idea here is that, okay, I'm going to show you some results on to proton transfer. What we get from the experimental side is the cross sections, and the main idea here is trying to connect these cross sections with the pairing operator. The pairing operator would be the quantity related to and that connect these the pairing between the nuclei in the nuclei. So this connection is not very straightforward. I must emphasize here that we have 2 contributions. One is the pairing phase, if the nuclei is a normal or superfluid, like tin. And the other, Lubin mentioned briefly, is the shape phase, if the nuclei is spherical or is deformed. This also plays a role when you try to connect it cross sections with the pairing operator. So it's just to give an overview. The key idea here is to 2 nuclear transfer cross sections. I'm trying to connect with this pairing response, not from the theoretical point of view, but I could give some hits on that. The pros that I'm approaching here is to use heavy ions, because this offers me a unique scenario to study not only the 2 proton, but with the same system I could be able to study the 2 neutron and also the neutron-proton transfer. So just for instance, I mean, the 2 neutron we could study on triton-proton reactions, but you cannot use the same probe to study the 2 proton reaction or the 2 proton pairing because you should go at least to helium-3 N reaction. Okay. The counts, I mean, this is a pro, and the counts are, well, when you deal with the heavy ions, you must include a large amount of mechanism configurations, single particle states, and also optical potential deformation. These offer a very difficulty on the theoretical point of view. Just like Lubin has mentioned about this in his talk here. So the point I would resume here is, okay, I'm going to use heavy ions. so this is a problem which I like to say it's a many channels, many problems. One problem for each channel. Yeah. And in principle, all reactions, all open reactions should be considered in your calculations. So, just for instance, I'm showing here, it's not the data that I'm using, but I'm putting here data for elastic scattering on neon 20, germanium 76, just to give an overview that exploiting the elastic scattering, we can put some constraints on the optical potential used to describe that. And then we move to the next channel with that, well, these are the elastic, then we move to the next channel, which is the inelastic scattering, and we try to not fit it, but we try to reproduce all the inelastic scattering using appropriate deformation, and we go step by step on these, trying to do it consistently. So, for instance, I have shown the elastic scattering. I have shown just the case for inelastic scattering, where we try to put some constraint on the input used for these calculations. Just to give you an idea, when it comes to 1 neutron transfer, for instance, this is an example for oxygen 18 on selenium 76. This is one of the systems that we are studying within the scope of this NUMEN project here. And this is just to give an idea also that going with the heavy ions, the excitation energy spectrum becomes difficult because you have contribution from the experimental point of view. You measure a peak, but these peaks represent a contribution of so many states, in some case here. And from the theoretical point of view, this imposes you the need to make the couplings with along many channels here. I'd just like to say that, again, each reaction channel means one problem more. So each reaction channel means one overlap function, one spectroscopic function, and you have to consider that. But we are, again, trying to do it consistently, use state-of-art structure model, shell model, and so on. Well, now I just briefly gave you an overview, the idea, what I'm thinking, and then I'm going to dive with these, with the data that I would like to say here. So just to start, this is 12 years ago. I mean, whenever I see this plot, I remember that I started doing my postdoc with this group. So this reminds me that I'm 12 years old here. So 12 years ago, we measured these 2 neutron transfer reactions, oxygen 18 here, on carbon 12. And we did it in 2 ways. Well, the one which is shown in this plot here, in this plot here. So these are the excitation energy regarding the carbon 14, and you see all the states here populated in these 2 neutron transfer reactions. But also we have measured 1 neutron transfer reaction using the carbon 13 target, and also populating this carbon 14, and this is shown here. So just to make clear, this is the 1 neutron transfer from carbon 13. This is the 2 neutron transfer from carbon 12, populating the same final states, and then you compare. And from this direct comparison, you see that some states here are highly suppressed, and this might give you some idea that, for instance, this first state here might be a single particle or so on. Well, when it comes to 2 neutron transfer, there is one more difficulty, because from the theoretical point of view, you might have this simultaneous transfer, but you might also have this sequential transfer here. So, and in this sequential transfer here, one of these steps is exactly this one that you can also measure in the laboratory here. So, putting all together, when I say putting all together, means checking the Alaskan, checking the Alaskan, the overlap, and so on. What Lubian and yes, Lubian and Van Telfer, I don't remember exactly, but Lubian has did this nice calculation here in which shows that the angular distribution for this ground state here on carbon 13 here is nicely reproduced by this cluster model that Lubin just presented ago here. So just to resume, from the angular distribution of these two Newton transfer reactions, the shape of this angular distribution might give you some hints about how this transfer proceeds, either by simultaneous transfer of two nucleons or by sequential. In this case, appears to be a simultaneous transfer of these two neutrons here. So what about now bringing this case of oxygen 16 silicon 28, the two proton transfer? Well, this, I must say that this was a very fortuitous data, because we started, at the beginning we were looking at other things. We were trying to study some giant resonances on silicon 28. So our first goal was to measure this giant resonance on silicon 28. At the end appears zero resonance, but the experimental setup is very good. So we got it not only the Alaskan, but also we got it many transfer channels in this case. And it's very fortuitous because silicon 28 in the shell model is a nuclei where you have these 1d5 shell filled. Oxygen 16 is a nuclei that has this 1p1/2 filled. So when you transfer, for instance, two protons from silicon, when you take away two protons from silicon, you are filling these two protons on the same shell in respect to oxygen 16, okay? So we are transferred to the same subshell here. So what we got, with silicon 28, we have measured the one proton picking up. I mean, the one proton is the process that feeds silicon 28, connects silicon 28 with aluminum 27. We also measured these two protons that connect silicon 28 with magnesium 26. And we also got this, we'll not discuss this, and also we also have measured this one deuteron transfer. These data are already analyzed, and we have some results, but I will focus more on these two cases here. So also, we not only measured the silicon 28, but also we have measured on aluminum 27 here. And this means that from the data with the aluminum, we also have this one proton transfer feeding this aluminum 26, and we also have this one neutron that feeds this aluminum 26. So I'm going to show some comparison of the experimental point of view, showing the results and the spectra for magnesium 26, populated by silicon 28, and also populated by aluminum 27. So first, what we did, we look at the elastic scattering. From the elastic scattering, we started to put the couplings and everything, just like I mentioned. The idea is that from the elastic, we put constraint on the optical potential and the deformations here. I'm going to move a little bit faster here and now. From the one neutron stripping that we also get, we put some constraints on the shell model used to describe the overlap functions between these two cases here. The main idea is that the same modular space used in the shell model for one Newton transfer will be the same used for the other transfer channels here. In this way, by looking at the Alaskan, the one Newton transfer, we get constraints on the optical potential deformation and the shell model on the modular space and in the interaction used to describe the other transfer channels here. So now moving to the results the results for 1 neutron transfer still. We have tested these three shell models to describe this 1 neutron transfer. This is the one with all of these subshells, is the one that provides the best descriptions of the data for this 1 neutron transfer. So for now on, I'm going to show results considering these kind of interactions for the other channels here. This is just to give an overview of the, let's say, the notebook for all these calculations if needed. So the proton picking up reactions. This one is the excitation energy spectra of aluminium-27, is populated in this transfer reaction here. Again, the bad things on heavy ions is that the energy resolution is not as good as in the light measurements here. So we have this region of interest that combines 1 and 2 states here, and here a region of interest 2 that combines 5 or 6 states here. But at least we can make some discussions based. We don't have these individual states, but we can make still some discussion based on this region of interaction here. So this second plot here is the excitation energy spectra for magnesium 26 has populated in this kind of reaction using this target here. And now I bring you these the same excitation energy spectra for magnesium 26, but in this case populated by a 2 proton transfer. So we should keep an eye here comparing these excitation energy spectra with these in the middle. So they are the same final nuclei, but populated with different. This one populated with a 1 proton transfer, and this one populated with a 2 proton transfer. Okay. So and this is my first hint from the experimental standpoint. When I look at this, and I see that we have this peak here in this first region of interest, and this one is missing. This gives me some hints that, well, perhaps the pairing between these 2 protons is playing a role here to describe this one, to describe this state here. Also, we need to take a look on this, and also we need to take a look on this region here that appears to be very important in this kind of. But I would like also to emphasize, this is just looking at the experimental data, no calculations. Is the thing that I like. So now from the experimental, from that spectra, we can get the cross sections. These are the cross sections for each of these 3 regions of interest, and then we look on the calculations, and these are the calculations here for considering the 1 proton transfer. Yes, the 1 proton transfer. And now, for the 1 proton transfer feeding the aluminium-26, so the results are, well, I would say not very good, but fairly good, acceptable, I would say. And now the 2 proton transfer here, when we are looking at this magnesium-26, again, the region of interest 1. Keep an eye on the red, on the blue, the sequential, and the simultaneous. For the first region of interest, it's hard to tell. But if you will look at the other 2 region of interest, and especially this one here, the region of interest 3, just give me back this. I'm talking about this one here, and you should compare with this one here. Okay. So when it comes to this region of interest 3, we see that this simultaneous transfer seems to be the mechanism that describes the experimental data here. Again, all these calculations are connected with the spectroscopic factors, and the spectroscopic factor is extracted from shell model using the space, the model space in the interaction that are constrained to other channels. So we are not playing with this model space here. So these are the 2 first hints that and I would like to proceed with the third and last hint that I would like to present here. But before, I need to discuss very briefly this concept of transfer probability, which is a semi-classical approach in which the transfer cross-section could be factorized in three quantities. One is related with the elastic scattering. The other is this transfer probability and a quantum correction. This quantum correction connects the initial and the final state. This is a semi-classical approach. To be honest, I still need to think a little bit more when we take this semi-classical approach to higher energy, to energies above the Coulomb barrier. Usually, this transfer probability, which is the one here, is expressed either on this reduced distant not closed approach or this big D. So this make easier to make the comparison here. The idea is that instead of comparing cross-section, might be good to compare with this transfer probability, because if you have two processes that are independently, the transfer for these two processes is just the square of the one step. So it's just like if you flip a coin, it's 50%. If you flip two coins, it would be 50 times 50. This is the main idea here. Well, I just mentioned that. So we have this one proton transfer because we have measured on aluminum. Yes, thank you. Because we have measured the aluminum, so we have the data for one proton transfer. These are the one proton probability, and what I'm showing here is just the square. When I make this curve, both this one and this one, when I make this square, this means that if the two proton transfer is independent process, when I put the data for two proton transfer, they should lie something around here. The difference is just the purple one is just a semi-classical approach here, and the blue is when I take these full couple reaction channel calculations here. So when I put the data for the two proton transfer, it appears to be that this so-called proton probability does not follow the expected independent to proton transfer. And this is my third hint here. So it could be that the transfer of these protons is proceeding by a simultaneous approach. And I think that I'm running out of time. This concept of transfer probability has been used also for other groups, especially in Legnaro, for this kind of study here. So you see here for the 1 neutron, 2 neutron in this kind of system here, they also make some discussion about this, but still, to be honest, still need to think a little bit more on this here. And also recently, last year, they also published some data on what they call the Cooper pairs on this system here for 1 neutron, 2 neutron here. And they quote, and I quote here, reactions between pair vibrational and pair rotational nuclei in this kind of nuclei correlation manifests when you add a pair or when you remove a pair. Just to summarize, and still some open question to myself. All of these that I'm presenting here today, is this somehow a measure of this PP correlation in transfer reaction? Well, to be honest, I'm still thinking on that. The two-nucleon transfer is a four-body problem. If you think of, is a four-body in which you have the core, the two particles, and the target. So maybe we should go on to a four-body approach for this transfer reaction then. And also, how do we compare these correlations between neutron, proton? This is still something that I'm still working on. I'm not showing here, but we also have data for this deuterium transfer, and the preliminary results indicate that also, in this case, the transfer proceed simultaneously, which means that might be the correlation between the proton-neutron in the transfer seems to be at the same order of magnitudes between the correlation of these two proton transfers. Just to recap, so this is, and I'm done, time is up here, and this is the resume of my talk here, and this is, I'm saying that it's under analysis, but it's done, okay? And thank you for your attention here.
Thank you very much, Roberto. Are there questions?
Thank you, Roberto. I mean, nice talk and stimulating. So now I'm surprised that PN, if we think about, I mean, maybe a short size pair coming out and be transferred, that you get the same probability for PP. According to what I remember from Nir presentation,
Yeah, I remember
PN
also.
pairs are much more probable than PP or NN.
But I'm not talking about short-range correlation. I'm just talking about the pairing in a mean field. So it's compared to, I think, in my opinion, I think that compared to me talk, I'm far away.
I was just thinking physically that you need something small to come together. If it is too large, how it will come together? This is, I'm just a naive picture that I had in mind.
But yeah, but when you say the two small, I miss.
The two nucleons together, I mean, to be, I mean, absorbed simultaneously, physically, in my mind, if you have them very far apart, it will be sequential. But if they are close by, they will be swallowed by the other nucleus together.
Mm-hmm.
And this is why I thought this could be related to short-range correlations, but your data say no. So, but I'm surprised with that.
Well, again, this is still that I would like to have more input from the theoretical point of view, because for one thing for sure is that I'm not allowed to say short-range correlation, because we are not saying about that.
I have a
So
very
Aurora,
a short range question.
Yeah.
there is Aurora with a question.
Yeah, but so if it is not a short range correlation, why do you speak about Cooper pair? Because I mean, a Cooper pair is something like, I mean, two fermions which stay very close, and somehow they change their nature.
Yeah, but the Cooper pair, if you bring to solid state, the Cooper between two electrons, you have the interaction between two electrons, and also the interaction, these two particles with the phonons of the lattice, with the field. So now here we have the interaction between two neutrons in the mean field of the nuclei.
Okay, this is the way to think about it.
We have Lubian and then Nir.
And then just to make the point that the pairing operator, you should work on this basis of Bardeen-Cooper-Schiffer basis. So connecting with this cross-section is not so straightforward.
It's not a question, it's more a comment. In the first papers we published, we call this pair correlation. I don't know if you realize that I didn't call more and pair correlation. Because when you use a basis to put your wave function of the two particles, you can have contribution from different shells. And they don't necessarily have to be near in order to be transferred, to be correlated in the moment you transfer that. So also, mainly when you talk about mean field theory, you talk about delta functions. In this case, you have to have finite range calculations. You have to consider, otherwise you don't have overlap of the initial and final state to produce the transfer cross sections. So just the comment.
Nir.
One comment, one question. First of all, regarding your comment, Cooper pairs should not be close together. they can actually, two particles can be correlated. One can be in Sao Paulo, the other can be in Rio. It still
no,
would be a
not
Cooper
that far.
pair. That depends on the scattering length. Yeah, so no, but it can still be far away, yeah. Second, can you go back to the, to these graphs, yes.
This one?
Yes. So they are actually fascinating.
Huh? Sorry?
They are fascinating. Can you explain to us again what do we see here?
Well, basically here they are showing that, this is the concept of transfer probability. So, and keep in mind that it's an approximation in which from the cross-section, the transfer cross-section, you extract this quantity.
Using this factorization ansatz.
Huh?
Using the factorization ansatz that you showed previously.
Yes.
Okay.
And then they are showing that, maybe this is not the best plot here, but they are discussing that this two-neutron transfer here, the probability is larger than the probability of individual transfer. So this might give you the idea that these two pairs they are correlated, and they are doing even more because this is the two-neutron removal, and the same happens with the neutron adding. Which, from the quantum point of view, is nice because it's a symmetry between particle and hole. So removing two particle is the same as putting two holes on the system. So this is more or less that, in short, what they are discussing in this pair, Köppen pair transfer here.
Thank you.
Again, to be honest, we could tell good Cooper when we are working on this BCS basis. But this is me, and I'm not nothing. This is me saying something about theoretician.
Okay. I'd say we thank very
Well,
much,
and
Roberto,
thank you. Sorry for
again,
being between you and your lunch.
and all the speakers of this morning, and we reconvene around 2 p.m.